So triangle rasterization, how could we do this? Well, there's a fairly obvious solution, which unfortunately is quite expensive. What you would do is, well, we have 3 points in 3D space, and given 3 points in 3D space, you can figure out the planar equation, and for each pixel, we can compute the equation of the 3D line that runs from the focal point and through that pixel center. And with these two equations, we can solve for where x, y, and z satisfies both equations. And this is doable, it's just expensive because first you're finding the equation line for every single pixel. That's actually the cheaper part, but then finding the intersection, that actually is a little expensive. More expensive at least than what we ideally would want to pay for each pixel. The other problem with this method is that actually what we really want to know about a pixel is not what is the corresponding 3D Cartesian coordinate. What we actually want to know is what is the corresponding barycentric coordinate on the 3D triangle. So this method is already expensive, but the process for translating from the Cartesian coordinate to the barycentric equivalent is even more expensive. So this is not ideal. Now, what would be really nice, for efficiency's sake, is having computed the appropriate value for 2 or 3 of these pixels, we could then use linear interpolation within the viewplane triangle to compute the rest. That'd be really nice. But because of how perspective works, because the lines of perspective fan out in a non-linear fashion, there's not actually a linear correspondence between the points in our two-dimensional triangle in the viewplane and the 3D triangle it corresponds to. It's just not a linear relationship. However, happily it turns out that there is a linear relationship between the so-called scaling factors, as I call them, and the points on the viewplane. By scaling factor, I mean the ratio of the focal length to the z, which is what we multiply the x's and y's of the 3D coordinates to get our corresponding points on the viewplane. Now, what this linear relationship means is that, say, on the viewplane, I have some point B of the viewplane that's halfway between A of the viewplane and C of the viewplane. Well, the corresponding point on the 3D triangle we'll call B. The scaling factor you multiply with B to get B of the viewplane, that scaling factor is halfway between the scaling factors we multiply on A and C to get A of V and C of V. So on the viewplane, say I already know that for these 2 points on the viewplane, I know what the scaling factors corresponding to those points are, in this case S of A and S of C, and I want to find the scaling factor that applies to the point halfway in between them. Well, it's just the average. I can do a linear interpolation. And so for the halfway point, it'd be S of A plus S of C divided by 2. So what this means then is if for a point on the viewplane, you know what the corresponding scalar factor for that point is, we can work backwards to find the x and y 3D coordinates by dividing by the scaling factor. To go from the 3D plane to the viewplane, we multiply by S. To go from the viewplane to the 3D plane, we divide by S. And thanks to the linear relationship between the scaling factors and the viewplane, we can compute the 3D coordinates corresponding to the pixel centers of our triangle in a quite more efficient way. For each of the 3 vertices of our 2D triangle, we have the x and y on the viewplane, and we also have the scaling factor for that point. And we have 3 of these 3D coordinates, so we can compute a planar equation. And be clear, it wouldn't be a plane that when graphed, it wouldn't look like the plane of the original 3D triangle. It would be different, but it would be something you can conceive of as a 3-dimensional plane. But given this planar equation, we then can plug in x and v values and get out a corresponding s value. And so for the box encompassing our 2-dimensional triangle on the viewplane, we find the viewplane coordinates for every pixel center, and we plug them into the planar equation to get the equivalent scaling factor for each of those pixels. And because we've said there's a linear relationship between the viewplane coordinates and the scaling factors, if I have 2 adjacent pixels, I know what their scaling factors are. I get the delta between them, and then I can just use that delta to fill in the rest of the pixels in the row or column. Let's say you have 2 pixels side by side, left and right. You can just add that delta to each subsequent pixel to fill in the s values, the scalar values, in the rest of the row to the right, and you could subtract to go in the other direction, to go left. And the same principle holds for columns. You find out the scaling values for a pixel and the one below it, you get the delta, and then you can add that to get the s values for all the way down, and then subtract to go all the way up. And so we're still paying the cost of finding the equation of a plane. There's a bit of work in finding the pixel centers on the grid of the view plane, though that's fairly trivial. And then we have to plug in at least 4 pixel center view plane coordinates into our planar equation to get the scaling factors. And then from there, we get the deltas between them and fill in the rest of the rows and columns. Like say we find the scaling factors for the top 4 pixels, the 2x2 square in the top left. Well, then you could fill in the left 2 columns, and now you have 2 pixels in every row, which you can find the deltas between to fill in the rest of every row. And through this process, we now have the scaling factors of every pixel. We, of course, also know what the view plane coordinates are at those pixels. So for each pixel, you take the x and y of the view plane, divide both by the scaling factor of that pixel, and we get the corresponding point on the 3D triangle. Now, we're not quite done because, as I explained, we don't really actually care about the 3D Cartesian coordinates. What we really want are interpolations of the vertex attributes. What are vertex attributes? Well, they can be whatever we want. We can just associate with each vertex some piece of data that's going to have some meaning in how we want to render. But the most common kinds of attributes that we attach to our vertices are RGB colors, UV texture coordinates, and normal vectors. Color values, as we'll see in an early exercise, can be used to determine what the colors of the pixels should be. And normal vectors we'll see considerably later when we bring in lighting calculations. You want to have the normals often influence how the lighting is performed. And generally what we want to achieve is a smooth lighting effect on our geometry so that it sort of disguises the angledness of our little triangles. But that'll come much later. So let's just consider texture coordinates. You want to paint a texture onto your triangles. Well, the way this is done is that we have some two-dimensional texture image, which is considered to have its own coordinate system of UV coordinates, where U is the horizontal axis and V is the vertical axis, with the origin usually in the bottom left, as you see here in the picture. And the idea is that, say, for a polygon, let's say a triangle, for each 3D vertex of our 3D triangle, it has an associated attribute, which is a UV coordinate, a point on the UV texture, such that the idea is that you want to imagine that portion of the UV texture painted on to the corresponding 3D triangle. And these triangles don't have to be the same shape, they don't have to be the same size. What we want is for the texture to be squashed and stretched as appropriate to fit onto the 3D surface. Now, for the points on the surface of our 3D triangle, there is a linear mapping to the corresponding triangle on the texture. For example, when we render an edge of our 3D triangle, the color we paint at the halfway point should match the color we see on the texture at the halfway point of the texture triangle's corresponding edge. So again, there's a linear relationship between the texture triangle and the 3D triangle, but as we've already said, because of the effective perspective, there's not a linear relationship between our 3D triangle and the viewplane triangle. Transitively then, there's not a linear relationship between our viewplane triangle and the texture triangle. So when on our viewplane, for a pixel, we want to figure out what the corresponding UV coordinate should be, we can't just do a straight linear mapping. We have to account for perspective. And it turns out, though, for reasons I won't mathematically prove, I'm vague on the proof myself, but it can be observed to be true, that for any attribute, whether we're talking about UV coordinates or RGB values or normal vectors, for any attribute of our triangle vertices that scale linearly within the triangle, then there's a linear relationship between our view plane and that attribute multiplied by the scaling factor. So for a similar example as before, we have some point B on the plane that's halfway between A and C on the plane, and the corresponding texture chord U value of B on the 3D triangle, that U value multiplied by the scaling factor of B, that is actually halfway between the same thing computed for A and C. If you took the scaling factor at A and its U coordinate value and the scaling factor at C and its U coord value, multiply those pairs together, and then average them, you would get the equivalent value of B's U times its scaling factor. And so for a point on the view plane, for a pixel, we've computed what U times the scaling factor for that pixel should be, and we also know what the scaling factor is. then we can divide out the scaling factor to get u. And the same logic for v. So then, to find the u-coords for each pixel, we find a planar equation for x and y of the view plane with u times the scaling factor instead of just a scaling factor like we did before. We find the chords of the pixel centers, and then we can use the planar equation to plug in x and y's for each pixel center to find the corresponding u times s for each pixel. Though again, we can use the same delta trick to optimize. We don't have to plug in x and y of every pixel center to get the u times s. Once we have just 4 of them, we can fill in the rest of the grid with cheaper addition operations. And so now we have u times s for every pixel. If we also have computed s for every pixel, then we can get the u's. We take for a pixel its u times s, divide by its s, and get its u. So in fact, we can do this same process for all of the vertex attributes. The r, the g, and the b of colors if our vertices have colors, the u's, the v's if we have texture coordinates, and if we have normal vectors, then the x, y, z's of those vectors. Now, this is beginning to sound a little costly because we'd have to compute all the scaling factors, and then in that case, if we had RGB colors, UV chords, and normal vectors, then you're talking about, well, that's 8 attributes that we'd have to do this whole process for, and that's getting a little expensive. Well, it turns out there's another thing we can do to cut down this workload. For a triangle, we can describe points on its plane in terms of what are called barycentric coordinates. The idea is that simply for each one of the vertices, you have an associated weight that is somewhere in the range of 0 to 1, and all of these weights, when summed together, always add up to 1. But then to find the x values, say you take the x's of each vertice and multiply the respective weights, and their sum gets you the x. Take the y's, multiply them by the respective weights, you get the y. It's basically describing points within a triangle by how close they are proportionally to each of the 3 vertices. So say if I have a barycentric coordinate which is 0.33, 0.33, 0.33, if they're all 1/3, then we're talking about the logical center of the triangle. If I have a barycentric coordinate of 1, 0, 0, then that means our point is one and the same as the vertex associated with the first weight, and so forth. So why do we care about barycentric coordinates? Well, if we have a point within or on the edge of a triangle described in terms of its barycentric coordinates, then for attributes associated with the vertices, we can find the interpolation by simply plugging them into the formula. We can simply multiply them by their respective weights and add them together, just like we find the x, y's, and z's from the weights. So instead of going through the whole process we just described, finding the corresponding attribute at that pixel, well, it'll generally be a little cheaper if we find the barycentric coordinate associated with each pixel of the view plane and use that barycentric coordinate to find the corresponding attribute value at that pixel. Now, if you're just computing one vertex attribute, it's cheaper just to directly compute it as we already described. But as soon as you have generally 3 or 4 or more, then there's a savings if instead we compute the barycentric coordinate. And beyond that, there's another really nice property of barycentric coordinates, which is that for barycentric coordinates of points outside of the plane, at least one of the weights, if not 2 or 3, are going to be negative. So if we compute the barycentric coordinates for a pixel, we have a very simple test then to know whether it is inside the triangle or not. If any of the values are negative, then it's not inside the triangle. So if we're going to compute the barycentric coordinate anyway to find the interpolated values of our vertex attributes, then we can also use it to determine which pixels are inside the triangle without having to do a separate edge function calculation, which is the other way of doing that. Okay now, but how do we find the actual barycentric coordinates? What's the cheapest way to do it? Well, happily it turns out that just like there's a linear relationship between the view plane and any vertex attribute times its associated scaling factor, well, for the barycentric coordinates times the scaling factor, there is the same linear relationship. And so given our view plane triangle, we know what the corresponding barycentric coordinates are. They're 1, 0, 0 for one vertex, 0, 1, 1 for the second vertex, and 0, 0, 1 for the third vertex. That's always the case with any triangle. Those are the 3 vertices in barycentric coordinates. And so we can find a planar equation expressing the relationship between the x's and y's of the view plane and the corresponding barycentric chord times corresponding scaling factor. Separately, we find the scaling factors for each pixel, and then by dividing out the scaling factor, we can get just the barycentric chord for each pixel. Actually, I should speak a little more carefully here. Of course, for a barycentric chord, there are 3 different weights. So you're finding 3 different planar equations, and for every pixel, you're finding 3 different barycentric weight times scaling factor values. And so you do end up doing 3 divisions, yes, but generally, particularly with many vertex attributes, this still works out to be cheaper. So the rasterization process is actually the trickiest part of the whole thing, and I did not give you an actual mathematical proof for why these linear relationships hold. You can kind of just intuitively see them, but I'm not giving you any formal proof. And as you may have picked up, there are many variations of how exactly to do rasterization. What I'm describing is not exactly how it's done in any GPU hardware. They all have variations. They do a lot of tricks to optimize it as much as possible. But what I've described is a workable process. You could do your rasterization this way. Fortunately, we don't really have to understand the details of this process because it is handled by the hardware for us. This is a part of the graphics pipeline that is hardwired. It is not programmable. There are, I think, some advanced cases where it is useful to know exactly what's going on or have some details about what's going on. But in vast majority of rendering, we just take it as faith. It's done for us. When the hardware rasterizes a triangle, what we're going to want in our pixel shader code is to have access to the vertex attributes of the triangle interpolated for this pixel. And that is what the hardware will do for us. It'll hand us the already interpolated values. And the interpolation, as I described, does account for perspective. So say when we get the interpolated UV chords for a pixel, they are perspective correct UV chords.